Log on, tune in, find out. Another good idea from Cambridge.
Is by Sam Sanders from the University of Gent. One of the rules is you should tell us how long you are here so we know how much we can be in touch. And his talk brings together non-standard analysis and constructive analysis.
Thank you, Russell. I'll only be here until Tuesday, sadly, because of other commitments. So, this talk is about my ongoing research in non-standard analysis, and please note the generous support of the John Templeton Foundation. Because 2012 is the Turing centennial, it's only fitting that we discuss the nature of algorithm, and that's what I'm going to do. I'll understand algorithm in the sense of finite procedure, explicit computation, that kind of stuff. Now, the technical definition of algorithm is sadly missing. If you ask computer scientists, philosophers, logicians, mathematicians, etc., what is an algorithm? There's no real one definition. Most people either refer to some framework or give ad hoc approximations. Now, in this talk, we'll try to partially formalize the notion of algorithm using non-standard analysis, the least likely candidate, and we'll consider some philosophical implications thereof. Non-standard analysis was used until very recently everywhere. It formalizes the intuitive calculus with infinitesimals, used to date in physics and used previously by the great names Newton, Leibniz, Euler, etc. For this talk we only need star n, which you can see on this number line. Star n has n as an initial segment, but lots of new stuff, not in the natural numbers. And well, the generic element is omega, 2 to the power of omega, we have then omega minus 1, and so on.
Omega doesn't mean a set of standard naturals or anything like that. To me it does.
No. Yeah, so some deviants use this to denote the set of natural numbers. No. These are the natural numbers. At some point they stop and, well, become what we call the infinite numbers. It's an extension. Of course, the natural numbers are the finite numbers. And all this together is star n, the hypernatural numbers. So again, once more, n, the finite or the standard numbers. Omega is the set, big omega is the set of infinite or non-standard numbers, and it's of course non-empty because that element is in there. I mean, it's really an element, you can take differences and stuff. One important principle which we shall not use is universal transfer. If a universal property is true for the natural numbers, then the same property is true for the hypernatural numbers. So the properties of n are translated to star n if you like. We won't assume this, but it will return later. So now, what does non-standard analysis have to do with algorithms, computation, and all that? Now, I will introduce a notion called omega invariance, which is reasonably close to algorithm, finite procedure, and the likes. Here, omega is the set of the infinite numbers, star n minus n. So a set is omega invariant if there's a quantifier-free formula such that for all infinite numbers, A can be written in this way. So A has a simple description. I mean, a quantifier-free formula, it doesn't get any simpler almost. But there is an infinite parameter, and the set has to be independent of the choice of the infinite number. That is extremely important. Here we have this infinite number, but it's independent of the choice, hence omega invariant. Now, it is not clear at first sight that this is somehow, that has anything to do with algorithm in general. Two theorems to convince you a little otherwise. First of all, given an omega invariant set A and the corresponding psi, for every k there is an m such that the truth of k in A is of course equivalent to the truth of psi, but this is also equivalent to psi k of m. So at some finite point m, we already know that k is in A or not, thanks to the properties of omega invariant sets. Hence, this omega invariance captures the notion of finite procedure reasonably well. At some finite point, it is known whether k is in A or not. This m can also be computed by an omega invariant function. It's kind of circular, but so is computability. Yeah?
Just trying to get an example of something like here, k is in the halting problem if it halts before.
But the halting problem isn't omega
Well,
invariant.
what's a good non-trivial example
Ah.
of a set like this?
There we go. Every delta 0, 1 set
Okay.
is omega invariant. So every Turing machine is an omega invariant procedure. However, this hinges on the fact that one adopts the right axiom system, classical logic, all that stuff. And given the right axiom system, probably the inverse is true. The delta 0, 1 sets are exactly the omega invariant sets in a very specific axiom system. Change the stray but a little from the true axiom system and it will be different.
What are you using the axiom system for here?
How do you mean? To
You haven't
formalize.
mentioned any logic so far.
Ah, well, that's because I only have half an hour and I'm actively sweeping under the carpet. But, well, there is this, Kiesler has this RCA0 star, non-standard version of RCA0, and there one can, or non-standard version of WKL0, there one can formalize this, but these systems are extremely sensitive to adding almost trivial axioms. That's why I say the right axiom system is very important. But, well, this is more a descriptive talk than a technical detail talk. Now, still, I mean, given this, one could reasonably believe that, alright, it stops, it stabilizes at some finite point, alright, maybe it's something like a finite procedure, this omega invariance. This is semi-convincing too, but, well, how well does it really capture algorithm? Now, we won't look at Turing machines and so on, because we'll look at constructive analysis. Eric Bishop, 1967, published his famous book on constructive analysis. Later on the system was called BISH, and later it was found out that the best underlying logic is intuitionistic logic. Then on the right hand side we have non-standard analysis based on classical logic, and we will provide a translation from Bishop to non-standard analysis. Of course, here central is the notion of algorithm. Something there's something computable, and something computable sends something to something computable. For example, A or B is that the fact that an algorithm decides whether A or B is true. Classically, A or B is just A or B, but here an algorithm has to say 0 or 1, this one or that one. So here, this will be the notion of an omega invariant procedure. So A, well, because we already have classical logic and the or and the and, we need a new symbol. This I call hyperdisjunction. An omega invariant procedure decides if A or if B. So written out in full, that would be, so A with some parameters, hyperdisjunction B with some parameters. That would mean that there is omega invariant psi such that for all standard parameters, if we have psi x omega, then this implies a of x, and in the negation case, this is. It's not exactly the most elegant or short thing, but that's how it works. Psi tells you true, then we have A. Psi tells you false, then we go for B. So that's how that works. That's a new kind of disjunction, hyperdisjunction, which is stronger than the normal one. There exists is also stronger intuitionistic logic, which means an algorithm computes a witness. On the other side, well, that has to be something similar. And that's actually not so difficult, because if we have a witness where this is delta 0, if there is a witness, then this function, the least n below omega, such that phi n, is omega invariant. Of course, if there is a finite witness, you can put any infinite number here, doesn't change things. And this is the omega invariant procedure to compute the witness. That's of course a trivial example. Then the real difficulty gets when we have A implies B. An algorithm converts a proof of A to a proof of B. On the other side, this should be translated as something similar. Note the quotes, however. Well, quote apparently. So how are we going to translate that? Well, here we go. If we have a universal quantifier, then we put a star there and replace that by normal implication. Why, oh why is that the case? Such is the case because in non-standard analysis there is many conservation results. If some standard theory plus non-standard axioms proves a universal formula, then the original theorem already proves the formula. So just adding some not too strong non-standard axioms doesn't change anything. We still prove this in certain cases. This is not a universal property. But there's many examples of this sort of thing. Now, a trivial corollary is that then also T plus NS proves the same formula but with a star. So if we can prove this, then we can prove the same formula with a star. And this is the inspiration behind this. A implies B is sending a proof of A to a proof of B. If there is a proof of this, then there's a proof of this. And similarly here. That's the inspiration. Note that I only work by analogy. This is not some realizability interpretation or something. Then, in case of an existential quantifier with a star, we lower the threshold. There is a witness below a fixed infinite number. This number is the same for everything. This is based on the idea, going back to Kiesler and other people, that infinite sequences or real numbers can be coded below any infinite number. So any information that's in an infinite object is already there below omega. So if there is a witness, there should be one below omega, because, well, you code up all the information below omega, so it must be there. Then negation is just what you expect it to be. And we can have some of the usual intuitionistic laws. The hypernegation of a universal formula is the existence of a witness, but only in star n. This is much weaker than the existence of a finite witness. Analogously, in intuitionistic logic, this is weaker than that, because this means we can compute a witness. This just means it's absurd that the universal formula holds. But it's just not because something is absurd that we can compute a counterexample. That's the idea here too. It's absurd that this holds. Look, there is a counterexample, but we can't compute one in an omega invariant way. Here, we can compute one. Here, we cannot. Now, so this is a translation from constructive analysis to non-standard analysis. Why is this a good or faithful or reasonable translation? Because, I mean, you can probably think of 10 other translations. This is a good translation because, as we will see, the non-algorithmic or the non-constructive principles behave in exactly the same way, both on the left and on the right side. You all know reverse mathematics, I hope. There is also this notion of constructive reverse mathematics. We work in the base theory BISH, and we look at non-constructive or non-algorithmic principles. And how do they relate? What are the minimal axioms, etc., etc. For example, the limited principle of omniscience, P or not P for sigma 1P, is equivalent to this. We can decide whether x goes to the right of 0 or to the left of 0. Brouwer rejected this because this would imply that a continuum can be split in two, and a continuum should not split in parts, because then it's not a continuum anymore. Similarly, these properties are equivalent to the monotone convergence theorem. A bounded increasing sequence converges. And to the Cantor intersection theorem, a sequence of nested decreasing sets, closed sets, has something in the big intersection. Now on the other side, well, what does this translate to? Well, kind of trivial, right? P or not P, P hyperdisjunction, hypernegation P. And that happens to be equivalent to x is bigger than 0, hyperdisjunction, hypernegation, x is smaller than 0. Aha! This is also equivalent to a version of MCT and CIT. Now, which version? Here, this limit of the bounded increasing sequence is computed by an algorithm. Here, it's computed by an omega invariant procedure. And the same here. There's a point in the intersection and we can compute it by an algorithm. This we can compute by an omega invariant procedure. So the similarities are obvious. Non-algorithmic and non-omega invariant behave in the same way. Ah yes, and all these things are actually well known. It's equivalent to the universal transfer principle we saw previously. Note that the universal transfer principle doesn't involve any of the hyper connectives. It doesn't involve this, or anything. It's just a principle from non-standard analysis. Now there's a lot of stuff under the constructive or the non-constructive sun, LLPO, which is essentially sigma 1 De Morgan's law. And this is well known to be equivalent to, well, the continuum weakly splits in two, and equivalent to nil. X times y is 0, then one of the numbers x or y is 0. And equivalent to the intermediate value theorem. Note that this is also non-constructive because this says if it's impossible that P and Q, then we can decide which one is true. Which one leads to absurdity, I'm sorry. It's a little too strong. So, how do we translate that? Well, hypernegation P and Q, hyperimplication, and so on. And apparently that's equivalent to the corresponding principles. And of course, again, here we compute this intermediate value by an algorithm. On the other side is computed by an omega invariant procedure. Again, non-algorithmic and non-omega invariant behave in the same way after our translation. But it even gets better. To prove this equivalence, we need an axiom of the continuum. It's impossible that x is bigger than 0 and smaller than 0 at the same time. Sounds obvious? To prove this equivalence, we need to use the fact that, well, hypernegation of x is bigger than 0 and x is smaller than 0. Not only do we get the same kind of phenomenon, we need to use the same kind of basic axioms. So, then there is Markov's principle, sigma 1 double negation elimination. And that's equivalent to the extensionality theorem. And of course, this translates nicely. Double hypernegation elimination, we have all these equivalences. Weak principle of limited something omniscience is equivalent to, well, the obvious real numbers and the fact that there's a discontinuous function. These equivalences translate literally, and here we have to think a little bit. From here to here, that's just replacing symbols. Syntactical mechanical translation. This is not exactly an automatic translation. Here we have to sort of think about the meaning of this to find a suitable translation. So you sometimes have to look at what something means. And Bishop was always hammering on the meaning of stuff. He had a point. Now there is also a weak Markov's principle for disjunction, the Fan theorem, BDN, and lots of more stuff. And mixed theorems. LPO splits in two, MP splits in two, lots of implications. And we all have these too. So I keep repeating it. Non-algorithmic and non-omega invariant behave in the same way. And that is our observation. So then algorithmic and omega invariant cannot be too far apart because, well, as I said, non-algorithmic and non-omega invariant are similar. So these two must be reasonably similar too. This is not an exact capturing, but Bishop's notion of algorithm wasn't exact either. It was vague. He wanted to make sure that his results were compatible with classical mathematics, intuitionistic mathematics, and recursive mathematics a la Markov. That's why he never wanted to say this is an algorithm. So, well, the best we can come up with is indirect approximations. Yes?
Give an example where this fails.
Yeah, not really. I have lots of examples where you say, well, I don't know how to translate this, or I don't know the equivalence yet, but I have no example where it really fails badly. So, some future research, and this is why I would be interested in talking to people here. Omega invariance can capture the notion of constructive function apparently. Can we do something more general? Can we somehow capture the notion of type, say in Martin Löw's type theory? Then, can we do something in bounded arithmetic? I'm particularly thinking of looking at the polytime functions in the Bell-Antoni-Cook framework, where you have normal and safe variables. There might be a way of capturing the notion of polytime using omega invariance. Then, philosophical implications. In the right framework, as I said, omega invariance captures Bishop's notion of algorithm indirectly and from the outside. Now, there's an analogy: brains in vats versus intuitionists and constructivists in nonstandard analysis. How does X know he's not actually sitting in Y? I believe Quine or somebody proposed, well, how do we know that we're not just a bunch of brains sitting in vats being manipulated by aliens or whatnot? I mean, who cares as long as there's not too much sorrow in our imaginary world? However, the constructivist or the intuitionist would suffer significant sorrow if he would learn that his stuff is actually non-standard analysis. Intuitionism and constructivism to some extent deny actual infinity. Non-standard analysis is the bulwark of actual infinity. So how does an intuitionist know, the couple that are left, how does he know that he's not actually doing some version of non-standard analysis? Because for him only finite stuff exists. He cannot judge whether something is infinite or finite. Now, why would there be a connection between non-standard analysis and constructive analysis? Why did the great Lord design things that way? I have nothing but a very informal and vague analogy there. Non-standard analysis looks like this: in star in, finite, infinite. It's, by the way, undecidable whether a number is finite or infinite. That's the thing I exploit to model this constructive stuff. Now, if f is a finite operation, we cannot go from the finite to the infinite via f, because you just can't. Now, in reading constructivist literature, one gets the impression that, well, there's of course the set of natural numbers, but there seems to be a chosen set n, based on the idea that, well, a number only exists after it has been constructed. These are somehow the constructed or the constructive numbers we are making in process of constructing. And some of them are non-constructive or non-constructible. We can never make those. They're only empty symbols. The same way we can never make omega out of finite blocks via finite operations. Well, because Bish is formalized in Heiting arithmetic with all finite types, such a number would seem like something we can never really construct. Because, well, epsilon 0 is the ordinal of piano arithmetic, proof theoretic ordinal. So constructing such a number would refer to the consistency of our own system, which is generally a bad idea. Now, there's also this vague notion of constructive operation, and we can never go from here to there. This is just a vague analogy, but I think it serves some purpose. Well, this one more. So this omega invariance may seem like something that is crazy and out of this world. Actually, it is not. In physics, we usually have constructive or computable results. A solution to a differential equation is given by, well, here is one. Either symbolically or numerically, it's computed. It's not the pure existence as we have in mathematics. There exists, it's just there exists. In physics, it comes with a witness. Now, why is physics that way? Hannes Diener once told me, well, because they do constructive analysis. That's a little ad hoc solution. So, well, on one hand, in physics, calculations are explicit and proofs of existence come with a construction. On the other hand, physicists still use some informal notion of non-standard analysis. Epsilon delta was never quite so popular there, or the hit it was in mathematics. The answer is omega invariance, actually. In physics, lots of mathematically dubious manipulation is alright, but the end result must have physical meaning. Physical meaning. Because it's physics. It's about the real world, or an approximation thereof. Now, an end result with physical meaning should not depend on the choice of the infinitesimals we used in deriving that end result, because infinitesimals are just calculus tools. If we use epsilon in our derivation, or epsilon squared, or the square root of epsilon, it should be exactly the same, because the real world should not depend on our choice of calculus tool. It should not depend on the choice of infinitesimal. However, infinitesimals are just the inverses of infinite numbers. Thus, being independent of the choice of infinitesimal is just omega invariant. And omega invariance, as we have seen, is close to the constructive notion of algorithm. And that's why things are so constructive or computable in physics, because of the independence of the choice of infinitesimal, i.e. omega invariance. This actually was pointed out by Kohn, or in a different way, but Kohn actually criticized nonstandard analysis for this. So I will skip over that. Thank you very much for your attention.
Just taking a moment to read the final thoughts here, actually. Meanwhile, do we have questions?
What can you actually do with what you have achieved? Can you actually now put theorems easier?
I haven't really looked into that, I must say. I mean, this is the state of the art, let's say. I took a survey paper of constructive reverse math and tried to translate it to non-standard analysis as much as possible, and it worked. Whether this gives rise to better mathematics, I don't know. Probably yes, but
Another question you had is kept omega invariant formulas and said that one example are your what was it? Delta 1 formulas.
delta 0, 1, yeah?
Delta 0, 1. Are there any other formulas? Or formulas which are not equivalent?
If delta 0, 1 formulas are omega invariant in classical logic. If you go to these hyperconnectives, then of course not all delta 0, 1 formulas in these hyperconnectives are omega invariant anymore, because you don't have Markov's principle or De Morgan's law in these hyperconnectives, because those are non-constructive principles. So yeah, it's in the same way there is recursive with classical logic or recursive with intuitionistic logic is different. And then again, whether you accept Markov's principle or not, and so on. So I don't know. Delta 0, 1 seems to be the upper limit, I think. Nothing beyond, like sigma 0, 1 certainly is not omega invariant. Probably that's the upper bound. I mean, kind of has to be, right?
I'm scratching my head, sorry.
Question in formation. Maybe one other thing right now, just at the very end, you were talking about physics using mathematically dubious methods. Is there any analogy to the situation where maybe physicists are talking about a variable that has real values, and they find that things work out better if they allow it to have complex values, even though they don't know what I means in this context?
Ooh, good question. I don't know.
I don't have a good example offhand.
Yeah.
But, this does happen.
Maybe you mean like with this renormalization where you have dimension 4 and then you take definition 4 minus epsilon and you let epsilon go to 0. That's one of those things, it works, but why does it work? I mean, it doesn't have any real meaning anymore. Dimension 4 minus epsilon. I can't think of an example either.
I mean, the situation with the complex numbers is different because none of us would say it's mathematically dubious. We
Yeah.
would say, oh, sure, use the complex numbers,
Now,
obviously.
with mathematics,
But, you know, physically, it's sort of dubious.
yeah. Now, mathematically dubious, I mean pushing limits through integrals, summing that's infinite sums that don't have any motivation and whatnot. Usually, this can be formalized because, well, it can be formalized because physicists don't talk about general mathematical objects. They're mathematical objects that have some bearing on the real world, and these are usually much nicer. But that's not really part of the point. The point is you can do all this stuff, but having a physical meaningful end result is usually used as a justification for the mathematical shortcuts you did. But it is essential, say, the physical meaning.
Boris Silber has this recent work that claiming to explain why things like using Feynman diagrams and those techniques that you were describing work using methods from stability theory and if you can believe it, uncountable uncountable categorical model theory and stuff. So he's got quite a lot of work demonstrating how those things can be derived, claiming to use the techniques of Warshawski and things like that. So if you can go to he's got some survey papers if you go to his homepage.
Yeah, that might be interesting. Thank you.
And he's only just up the road somewhere.
Ah,
England's a small place.
Belgium is a small country.
Yeah, thank you very much.